Hi everyone, this is Przemysław Koprowski again. Welcome to the second lecture of the mini course Computational Mathematics. On the previous lecture you learned some fundamental algorithms that allows us to deal with polynomials. Among them you learned two methods for multiplying polynomial. The standard long multiplication that you know already from the school, which turned out to be the slowest one. It has a quadratic asymptotic complexity. And then subsequently you learned Karatsuba multiplication, which is evidently faster because it has a asymptotic complexity of n to the power 1.6. The aim of today's lecture is to introduce you to so-called fast Fourier transform, a very important tool in analysis and calculus, and which has some particular applications to computational mathematics. One of such particular applications is a new, completely different method for multiplying polynomials, which is based on fast Fourier transform. And this method is definitely superior one because it has an asymptotic complexity n log n.
First, let me recall the notion of a Fourier series, which I strongly believe that you know from your previous studies. In a nutshell, the Fourier series is a way to decompose a periodic function into sines and cosines, to detect which infrequencies of the sines and cosines appear in a given periodic function. To be more precise, let's f be a periodic function, and then a Fourier series is a functional series given in a following way. It's a sum of an times cosine plus bn times sine, where the parameters of sine and cosine, the arguments, are scaled in such a way to be coherent with the period of f. So if f is a function, a periodic function of a period L, which is absolutely integrable on the interval minus L over 2 to L over 2, so it's absolutely integrable on its period, then the functional series given by the formula that you see on screen, so as I said, is a sum of sines and cosines, where the arguments an and bn are given by these two intervals. Such a periodic series, such a functional series is pointwise convergent to f. If we in addition assume that f is C2 smooth, so it is continuous, it's differentiable, its first and the second derivative are continuous as well, then this convergence is uniform. We'll observe how it works on a simple example. Take a function sine of sine. It is of course not continuous. In fact, this graph that you see here is improper. There should be no vertical lines here. It's an error that Sage software does here. The Sage software, this graph was automatically generated by Sage, and for whatever reason Sage introduced these vertical lines that should not be here. So this the graph of f consists of horizontal lines interleaved 1 and minus 1. So the interleaved interval of each of length pi, on one of this interval the function takes the sine 1, on the other it takes sine minus 1. So let us compute a couple of first partial sums of the Fourier series. First of all, the sum f1, so just one term of the Fourier series, it's just 4 sine x over pi. So it's just a standard sine, just scaled to fit to have a appropriate height. As you can see, it's not very similar to our original function. However, it has, of course, the same period. Now let us compute the fifth partial sum of this Fourier series. So it's sine x times 4 over pi, then sine of 5x times 4 over 5 pi, and sine over 3x times 4 over 3 pi. As you can see, it somehow to some degree resembles the original function. So let us compute some more partial sums. Now the next one, f10, is the sum over the odd numbers, over the odd integers from 1 to 9, sine nx times 4 over n pi. So it's 4 sine x over pi, 4 sine 3x over 3 pi, 4 sine 5x over 5 pi, and so on till 4 sine 9x over 9 pi. Observe that there is that in this particular example we don't have even coefficients. That's clear because our function is built completely from sine. There is no cosine appearing here, so we have no cosine, so this cosines does not turn out here. And let's compute one more partial sum, f30. So it's a sum of very similar form as before. It's a sum over the odd indices from 1 to 29, sine of nx over n pi times 4. As you can see from this graph, the graph of this partial sum is already quite similar to our original function. So it shows us how this convergence works. So we started with a sine, and adding more and more frequencies, we were able to build a function that closely resembles our original function. Although the original function was not even continuous, this function, this Fourier series, is of course continuous. It's analytic. It has all the derivatives with whichever derivative it's first, second, and so on and so on. You can count all the derivatives up to infinity. Nevertheless, its graph is very similar. It is pointwise convergent to our function f. In order to introduce Fourier transform, which is the subject of today's lecture, we will use a well-known identity which relates sine, cosine, and exponents, namely exponent of I times alpha is the same as cosine alpha plus I sine alpha. This is a well-known identity which let us write a complex number in exponential form instead of trigonometrical form. If we use this identity, we can convert our definition of a Fourier series to an alternate form, which is also a Fourier series. It's just a different way of writing a Fourier series, but it's more convenient for us. It's a sum from minus infinity to plus infinity, one coefficient. Now we have one coefficient Cn times e to the exponent I times n times t times 2 pi over L, where L is the period of our function. So the last part is just scaling, so the periods of sine, cosine, and our function f are the same. And the coefficient Cn is given by this integral formula that you see on the slide. So now we can go to Fourier transform. So what is a Fourier transform? We can think of a Fourier transform as a continuous counterpart of a Fourier series. Whereas in a Fourier series we have a sequence coefficients. Now, instead of a sequence of coefficients, we will have a function defined and on continuous domain. So we can think about it in this way. The Fourier series just detected discrete periods in a given function f, and the Fourier transform detects all the possible frequencies which appear there. So we had Fourier coefficient C1, C2, C3, and so on. Now we have a function which takes all the possible arguments between 1 and 2, 2 and 3, and so on. So we will have C at 1/2, C and 3/8, and so on and so on. So this will be a continuous way of analyzing a function. In fact, the Fourier series is used to analyze existing function to detect frequencies which appear in a given function. So geometrically speaking, a Fourier transform converts a function from the spatial domain, where we have a function defined on certain arguments, to the frequency domains, which have a function defined on frequencies. It's a popular interpretation of a Fourier transform. We just extract the different frequencies which appear in a given function. So a formal definition looks like this. Assume that we have a function which is integrable. When we define a Fourier transform of this function, that we denote f hat, which is a function from the reals to the complex numbers, and it is defined by this formula. So it's integral from -infinity to the infinity, f of t times e to the power minus I 2 pi t times t. Here the lowercase t is the variable of the integral, and capital T is the variable on which the Fourier transform with f hat is defined. Along the way, we can define also the inverse Fourier transform, which is defined by almost the same formula. Again, returning to our interpretation, the inverse Fourier transform take a function defined on frequencies and converts it into the corresponding function defined in a spatial domain. The formal definition of the inverse Fourier transform differs from the definition of the inverse transform only in the sign of the exponents. If you look at the formula is absolutely the same. The only difference is that in the Fourier transform, in the exponents we have minus I times 2 pi t, and in the inverse function we have plus I times 2 pi times t times t. It's the only distinction between these two notions. However, as I said, the interpretation is that one takes the function defined in a spatial domain and converts into function defined in the frequency domain, and the other one works the other way, takes a function defined in frequency domains and converts it to a function defined in a spatial domain. The most important identity concerning the Fourier transform is the theorem by Fourier himself, which says that if we have a function which is continuous and, well, let's say nice enough, there are a couple of possible sufficiently conditions that we can put here. For the purpose of this lecture, I assume that f is absolutely integrable. So f is continuous and absolutely integrable. So it's integrable when we take the absolute value of f, and its Fourier transform is absolutely integrable too. When the Fourier transform and the inverse Fourier transform are true inverses of each other. So if we take f, we compute its Fourier transform, and then we compute its inverse Fourier transform, we arrive back at f. This is a fundamental identity due to Fourier. We will not prove it in this lecture because we will not use this version of the identity. This is only a context to show you where this all the theory that we will develop fits in. And so let me return to our example of function sine of x. So we again have this improper graph of this function. So it's a proper graph except the vertical lines which the computer generated improperly. And since the formula for the Fourier transform is explicitly given by the integral, we can explicitly compute, symbolically compute the Fourier transform of this function f, and this is a function capital F or f hat, because both notation are common. The Fourier transform is either denoted by hat or by going to a capital letter. It's the sum of these three fractions, so it's minus I over p times t plus e times exponent of 2i p squared t over 2 pt plus the plus I times the exponents of the inverse of the opposite number, means minus 2 I p squared t. And the graph of the imaginary part, of course the imaginary part is the only which counts here, because there is no cosines here, there are only sines. The graph of the imaginary part is depicted below. As you can see, this first maximum refers to the fact that the frequency, the main frequency of our function is the same as the frequency of sine. It's just 1 over 2 pi, and this is this first maximum, and all the other local maximas on this graph correspond to successive periods of f, since okay, the 2 pi is the period of f, but 4 pi is another period of f. This is the second maximum on this graph. 6 pi is another period of f. This is the third maximum of this graph, and so on and so on. So if we decompose, we can, as we saw before in this previous part of this example, we can decompose our function into infinite sum of sines with different frequencies, and successive terms of this series have smaller and smaller coefficients, and these exactly correspond to this graph. So if we decompose it, this is the way of decomposing it. And now I will overimpose on this graph, I will overimpose the coefficients of the Fourier series that we computed in the previous example. So these dots that you can see now are the coefficients of the Fourier series. They are scaled to, so the scales of the two graphs are made coherent, so they agree with each other, but except the scaling I did nothing else. I just scaled the two graphs so they fit together, and these are the coefficients Bn, so these coefficients which correspond to sines, because only sines that appear there. As you can see, they exactly fit on the graph of the Fourier transform. That's why I said the Fourier transform is a continuous counterpart of the Fourier series. The Fourier series just detected it in discrete places. It just detected the discrete values of discrete frequencies, discrete periods of our function, and the Fourier transform just detected everything. It just described the whole behavior of the function f in the frequency. Now, when we have this thing done, when we discuss the interpretation of the standard Fourier transform, we can pass to what is the real subject of today's talk, what we are really going to talk about. Because so far we just define a context. I just recalled the notion of a Fourier series and a Fourier transform to just give you a proper perspective on what we are going to discuss, because the main subject is the discrete Fourier transform. So now when we know what is a standard Fourier transform, we can discretize it. So the Fourier transform was a function with both the domain and codomain that were the whole real line. So they were so it has a continuous domain and continuous codomain. Now the discrete Fourier transform discretizes both the domain and the codomain. So what we do, in place of a function, we have a sequence. That's the discretization of a domain. In place, as a result, in place of integral, we need to take a sum. In place of function, we need to we have a sequence. In place of a function at a given point, we take a coefficient of a sequence, one of the entries of a sequence, and we do not do any other changes. We just convert this formula that you see on the screen from the language of functions, from the continuous language to the discrete language, to the language of sequences. So as I said, we change the integral to a sum. So in place of a function defined on real numbers, we have a finite sequence of, let's say, real numbers. As a result, the result is no longer a function, it's again a discrete, a finite sequence. And so the integral was replaced by a sum, the value of a function and the value of a transform is replaced by a given coefficient, given entry of a sequence. That's all. Now when you recall the definition of the inverse Fourier transform, it differs from the Fourier transform just by the sign of the exponent. Here is the same with one exception. If we have again a sequence, I will use the capital letters to emphasize the fact that we are now in a frequency domain. We have a sequence of elements. We define its inverse discrete Fourier transform or discrete inverse Fourier transform just to be a sequence of the same length of elements defined by almost the same formula as before. Again, we change the sign of the exponent. We had minus I, now we have I, but as you can see, there is one more change. There appeared fraction 1 over n. Let me comment it for a moment. This fraction must appear there because in order to the analog of the Fourier theorem to be satisfied. However, it may appear in any place. So there is a number of, well, in fact there are 3 different conventions concerning the definition of a discrete Fourier transform and inverse discrete Fourier transform. So one convention, the one which I use here, is to put this 1 over n in the discrete Fourier transform. But it's equally justifiable to put this 1 over n in the Fourier transform. So at that time we have 1 over n in the forward Fourier transform, and there is no fraction in the inverse Fourier transform. And then there is a third convention which prefers to make both definitions symmetric, and those guys put 1 over square root of n both in the forward and inverse Fourier transform, and this is equally valid definition. All these definitions give rise to the same theory, so this is just a matter of taste. Here in computational mathematics, especially in symbolic computations, we prefer to avoid the square roots or generally higher radicals as long as it's possible. So it's better to put 1 over n in the discrete Fourier transform than to put 1 over square root of n in both forward and inverse Fourier transform. But honestly speaking, from mathematical point of view, both definitions are equally correct and they give exactly the same result. Now we will do one more step to generalize our definition to make it work with not only real sequences but other too. Let us look at this exponent which appears in the definition of the Fourier transform and inverse Fourier transform. This is e to power 2 pi n 2 pi chi n over n. So if we put this k outside, we can think of e to the power 2 pi n and exponents of this number. So what is this number? If we think for a moment, if we recall how the complex numbers look like, this is exponential form of the number cosine 2 pi over n plus I sine 2 pi over n. So this is a number whose argument is 2 pi over n. This lies on the unit circle and its argument is 2 pi over n. So now when we recall what is the geometric interpretation of multiplication of complex numbers, especially exponentiation of a unit complex numbers, we see that the nth power, when we multiply the number, we rotate it. We add arguments to each other. So this is the Demauve formula. So if this number lies on, it is 1/n of a circle. It's 1/n of a circle. We need to exponent. We need to multiply it by itself n times to finish this circle, to get back to 1. So this is a number, so this omega is a number such that the nth power of omega is 1, but any other powers, any other positive powers but strictly less than n is not 1, is distinct from 1. Such a number is called a primitive root of unity. In this case, a complex primitive root of unity. More generally, given any ring R and a number and a positive integer n, an element omega is called a primitive root of unity of degree n if omega to the nth power omega, nth power of omega is 1, but all the earlier powers are different from 1. Such a number is called a primitive root of unity of degree n. And now, when we have the notion of a primitive root of unity, we can define the discrete Fourier transform in terms of a primitive root of unity. This way, we are free to use any ring of coefficients, not necessarily real complex numbers. We are not longer limited to work with just complex numbers. We can work with any ring, any coefficient ring in which we can find a root of unity. So now the general definition of a discrete Fourier transform is the following one. We have a ring and we have a primitive root of unity of degree n. So recall me, it's a number. Let me recall that it's a number such that its nth power is 1, and this is the first power where omega to the n becomes 1. Now we take a finite sequence of the length n, so it's f0, f1 up to fn minus 1, and we define its discrete Fourier transform to be a sequence of the same length but defined by the formula that the nth, or here is lowercase n. Maybe I should have written j here. So let me say fn hat is the sum fk times omega to minus chi n. The inverse Fourier transform, inverse discrete Fourier transform, differs from the definition of a Fourier transform in just two places. First of all, we change the sign of the exponents, so no longer minus chi n, here is chi n, and we put this fraction 1 over n into the formula because it must be in one of these two formulas, and I prefer to put it in the discrete Fourier transform. So now when we have a formal definition of a discrete Fourier transform, let me compute one example. I will compute this example in three different ways. First of all, I will compute it just straight from the definition. So to make this example short and simple, let me take the following sequence, just 1, 2, 3, 4. So f will be the sequence 1, 2, 3, and 4. As you can see, the length of this sequence, so our number n is 4, and we are working here, we are working just over the complex numbers, so we need a number such that its fourth power is 1, but no earlier power is 1. Of course, such a number is I, so omega is just I. So let me compute now the Fourier transform, discrete Fourier transform of this. So it will be a sequence consisting again of 4 elements, such that f0 hat is a sum from k equal 0 up to n minus 1. So n is 4, n minus 1 is 3. So from 0 to 3, it is fk, here is k, maybe it's not very visible, times I to the power minus k 0, but 0 times anything is 0, so it's just a sum f0 plus f1 times f plus f2 plus f3. So it's 1 plus 2 plus 3 plus 4, so it equals 10. So the first coefficient of the discrete Fourier transform f equals 10. So let us compute the next coefficient, f1 hat. It's again by the same formula. This is sum from k equal 0 up to 3, fk times I to the power minus k times 1, so minus k. So what is? It's f0 times I to the 0th power, so f0 times 1, so f0, plus f1 times I to minus 1, so 1 over I, plus f2 times I to the minus 2nd power, so 1 over I square, plus f3 times I to the power minus 3, so it's f3 times I 1 over I cube. So what is this? It's 1. Now 1 over I is minus I, so it's minus 2I. f2 is 3I square is minus 1. 1 over minus 1 is minus 1, so it's minus 3. And 1 over I cube is I again, so it's plus 4I. So if we now group together the imaginary part and the real parts, we see that we have 1 minus 3, so it's minus 2, and minus 2I plus 4I is 2I, so it's plus 2I. So the second coefficient of the discrete Fourier transform is minus 2 plus 2I. So let us compute now the f2 hat. And again, the same formula. It's sum from k equals 0 to 3 fk times I to minus k times, and now we have index 2, so minus k2. So what it is? Again, just f0 plus f1 times 1 over I square plus f2 times 2f2 times 1 over I to the 4th power plus f3 times 1 over the 6th power of I. So again, this is 1. Now I square is minus 1, so minus 2 plus the 4th power of I is again 1, so it's plus 3. And the 6th power of I is again minus 1, so it's minus 4. So this is minus 1, so it's minus 2. So this equals minus 2. And now the last coefficient of the discrete Fourier transform, this is f3 hat, is again the same sum. It's k equals 0 up to 3 fk times I to the power minus chi times 3. So this is f0 plus f1 times 1 over I cube plus f2 times 1 over the 6th power of I plus f3 times 1 over 9th power of I. So this is 1. Now 1 over I cube, we already know that it's plus 1. It's plus I, so it's plus 2I. Now the 6th power of I is minus 1, so it's minus 3. And now we have minus I, so it's minus 4I. So again, we just collect the imaginary parts together and real parts together, and what we got is minus 2 minus 2I. So all in all, the discrete Fourier transform of our f is a sequence consisting of 4 elements. It's 10 minus 2 plus 2I minus 2 minus 2 minus 2I. That's it. So this is a way of computing the discrete Fourier transform just directly by definition, just straight out of definition. In a similar way as we had for the standard Fourier transform, for the discrete Fourier transform there also holds an analog of the Fourier theorem. So if we have a ring and a primitive root of unity of degree n, therefore any sequence of length n, the discrete Fourier transform and the inverse discrete Fourier transform are opposite of each other. They are inverses. That's why that's the name inverse Fourier transform comes from. Observe that unlike in the standard Fourier theorem, here we have no special assumption. In the standard Fourier theorem we had to assume that f was absolutely integrable. Here we do not put any special assumption because they are vacuously true. Recall that here we deal with finite sequences. A finite sequence is always summable. So the analog of the condition that the f must be absolutely integrable, the discrete analog would be that f is absolutely summable. But when we have only finitely many numbers, then we can always sum finitely many numbers. We can just add these numbers to each other and we have a sum. So the condition that f is absolutely summable is always true. If it's always true, we don't need to put it in the proposition, so we don't have any special assumptions here. Before, just a minute or two ago, I computed the Fourier transform of a sequence using just the definition. Now here on this lecture, in this course, we are dealing mostly with polynomials. This course is in most part it deals with operations, algorithms on polynomials. So let's take a polynomial and treat it as usually as a sequence of coefficients, exactly as we did before. On the last lecture we have a polynomial, but we treated it internally as a sequence of polynomials. So let's do it again. Take a polynomial, think of it as a sequence of coefficients, and we can ask what is the Fourier transform of these polynomials, of this sequence of coefficients of a polynomial. And now this observation that you see on the screen right now says that a Fourier transform of a sequence of polynomials, a sequence of coefficients of a polynomial, is nothing else but the values of this that this polynomial takes in a successive powers of the inverse of omega. So the Fourier transform of f is just f at 1 over omega, f at 1 over omega square, and so on and so on. So let me show you the proof of this fact. By the very definition, f hat is so the discrete Fourier transform is the sequence f0 hat up to fn minus 1 hat. Now let the polynomial f is of a form f0 plus f1x plus f2x squared, and so on up to fn minus 1 x to the power n minus 1. So by the way we define the Fourier transform, discrete Fourier transform, fj hat was just the sum of k equal from 0 up to n minus 1. Here we had fk times omega to the power minus kj. Okay, but we can write it explicitly this way. So first it's f0 times omega to the power 0 plus f1 times omega to the power minus j plus f2 times omega to the power minus 2j, and so on and so on. The last one is fn minus 1 times omega to the power minus n minus 1 j. But we can write it also this way. This is f0 plus f1 times 1 over omega to the jth power plus f2 times 1 over omega to the jth power and the square of it plus and so on plus f n minus 1 times 1 over the jth power of omega to the n minus 1. And now if we look here and here, we immediately see that this thing is nothing else but f over 1, f on the 1 over jth power of omega, which is exactly what the thesis, what the assertion says. So this way we have proved that. Now we will do one more step to generalize our definition, to make it work with not only real sequences but other too. Let us look at this exponent which appears in the definition of the Fourier transform and inverse Fourier transform. This is e to power 2 pi n 2 pi chi n over n. So if we put this k outside, we can think of e to the power 2 pi n and exponents of this number. So what is this number? If we think for a moment, if we recall how the complex numbers look like, this is exponential form of the number cosine 2 pi over n plus I sine 2 pi over n. So this is a number whose argument is 2 pi over n. This lies on the unit circle and its argument is 2 pi over n. So now when we recall what is the geometric interpretation of multiplication of complex numbers, especially exponentiation of the unit complex numbers, we see that the nth power, when we multiply the number, we rotate it. We add arguments to each other. So this is the Demauve formula. So if this number lies on, it is 1/n of the circle. It's 1/n of a circle. We need to exponent. We need to multiply it by itself n times to finish this circle, to get back to 1. So this is a number. So this omega is a number such that the nth power of omega is 1, but any other powers, any other positive powers, but strictly less than n, is not 1, is distinct from 1. Such a number is called a primitive root of unity. In this case, a complex primitive root of unity. More generally, given any ring R and a number and a positive integer n, an element omega is called a primitive root of unity of degree n if omega to the nth power omega, nth power of omega is 1, but all the earlier powers are different from 1. Such a number is called a primitive root of unity of degree n. And now, when we have the notion of a primitive root of unity, we can define the discrete Fourier transform in terms of the primitive root of unity. This way, we are free to use any ring of coefficients, not necessarily real complex numbers. We are not longer limited to work with just complex numbers. We can work with any ring, any coefficient ring, in which we can find a root of unity. So now the general definition of a discrete Fourier transform is the following one. We have a ring and we have a primitive root of unity of degree n. So recall me, it's a number. Let me recall that it's a number such that its nth power is 1, and this is the first power where omega to the n becomes 1. Now we take a finite sequence of the length n, so it's f0, f1 up to fn minus 1, and we define its discrete Fourier transform to be a sequence of the same length, but defined by the formula that the nth, here is lowercase n, maybe I should have written j here, so let me say fn hat is the sum fk times omega to minus chi n. The inverse discrete Fourier transform differs from the definition of a Fourier transform in just two places. First of all, we change the sign of the exponents, so no longer minus chi n, here is chi n, and we put this fraction 1 over n into the formula because it must be in one of these two formulas, and I prefer to put it in the discrete Fourier transform. So now when we have a formal definition of a discrete Fourier transform, let me compute one example. I will compute this example in three different ways. First of all, I will compute it just straight from the definition. So to make this example short and simple, let me take the following sequence, just 1, 2, 3, 4. So f will be the sequence 1, 2, 3, and 4. As you can see, the length of this sequence, so our number n is 4, and we are working here, we are working just over the complex numbers. So we need a number such that its fourth power is 1, but no earlier power is 1. Of course, such a number is I. So omega is just I. So let me compute now the Fourier transform, discrete Fourier transform of this. So it will be a sequence consisting again of 4 elements, such that f0 hat is a sum from k equal 0 up to n minus 1. So n is 4, n minus 1 is 3. So from 0 to 3, it is fk, here is k, maybe it's not very visible, times I to the power minus k 0, but 0 times anything is 0, so it's just a sum f0 plus f1 times f plus f2 plus f3. So it's 1 plus 2 plus 3 plus 4, so it equals 10. So the first coefficient of the discrete Fourier transform f equals 10. So let us compute the next coefficient, f1 hat. It's again by the same formula. This is sum from k equal 0 up to 3, fk times I to the power minus k times 1, so minus k. So what is? It's f0 times I to the 0th power, so f0 times 1, so f0, plus f1 times I to minus 1, so 1 over I, plus f2 times I to the minus 2nd power, so 1 over I square, plus f3 times I to the power minus 3, so it's f3 times I 1 over I cube. So what is this? It's 1. Now 1 over I is minus I, so it's minus 2I. F2 is 3, I square is minus 1, 1 over minus 1 is minus 1, so it's minus 3. And 1 over I cube is I again, so it's plus 4I. So if we now group together the imaginary part and the real parts, we see that we have 1 minus 3, so it's minus 2, and minus 2i plus 4i is 2i, so it's plus 2i. So the second coefficient of the discrete Fourier transform is minus 2 plus 2i. So let us compute now the f2 hat, and again the same formula. It's sum from k equals 0 to 3 fk times I to minus k times, and now we have the index 2, so minus k2. So what it is? Again, just f0 plus f1 times 1 over I square plus f2 times 2f2 times 1 over I to the 4th power plus f3 times 1 over the 6th power of I. So again this is 1. Now I square is minus 1, so minus 2 plus the 4th power of I is again 1, so it's plus 3, and the 6th power of I is again minus 1, so it's minus 4, So this is minus 1, so it's minus 2. So this equals minus 2. And now the last coefficient of the discrete Fourier transform, this is f3 hat, is again the same sum. It's k equals 0 up to 3, fk times I to the power minus chi times 3. So this is f0 plus f1 times 1 over I cube plus f2 times 1 over the 6th power of I plus f3 times 1 over 9th power of I. So this is 1. Now 1 over I cube, we already know that it's plus 1. It's plus I, so it's plus 2I. Now the 6th power of I is minus 1, so it's minus 3. And now we have minus I, so it's minus 4I. So again we just collect the imaginary parts together and real parts together, and what we got is minus 2 minus 2I. So all in all, the discrete Fourier transform of our f is a sequence consisting of 4 elements. It's 10 minus 2 plus 2I minus 2 minus 2 minus 2I. That's it. So this is a way of computing the discrete Fourier transform just directly by definition, just straight out of definition. In a similar way as we had for the standard Fourier transform, for the discrete Fourier transform there also holds an analog of the Fourier theorem. So if we have a ring and a primitive root of unity of degree n, therefore any sequence of length n, the discrete Fourier transform and the inverse discrete Fourier transform are opposite of each other. They are inverses. That's why that's the name inverse Fourier transform comes from. Observe that unlike in the standard Fourier theorem, here we have no special assumption. In the standard Fourier theorem we had to assume that f was absolutely integrable. Here we do not put any special assumption because they are vacuously true. Recall that here we deal with finite sequences. A finite sequence is always summable. So the analog of the condition that the f must be absolutely integrable, the discrete analog would be that f is absolutely summable. But when we have only finitely many numbers, then we can always sum finitely many numbers. We can just add these numbers to each other and we have a sum. So the condition that f is absolutely summable is always true. If it's always true, we don't need to put it in the proposition, so we don't have any special assumptions here. Before, just a minute or two ago, I computed the Fourier transform of a sequence using just the definition. Now here on this lecture, in this course, we are dealing mostly with polynomials. This course is in most part it deals with operations, algorithms on polynomials. So let's take a polynomial and treat it as usually as a sequence of coefficients, exactly as we did before. On the last lecture we have a polynomial, but we treated it internally as a sequence of polynomials. So let's do it again. Take a polynomial, think of it as a sequence of coefficients, and we can ask what is the Fourier transform of these polynomials, of this sequence of coefficients of a polynomial. And now this observation that you see on the screen right now says that a Fourier transform of a sequence of polynomials, a sequence of coefficients of a polynomial, is nothing else but the values of this that this polynomial takes in a successive powers of the inverse of omega. So the Fourier transform of f is just f at 1, f at 1 over omega, f at 1 over omega square, and so on and so on. So let me show you the proof of this fact. By the very definition, f hat is so the discrete Fourier transform is the sequence f0 hat up to fn minus 1 hat. Now let the polynomial f is of the form f0 plus f1x plus f2x squared and so on up to fn minus 1 x to the power n minus 1. So by the way we define the Fourier transform, discrete Fourier transform, fj hat was just the sum of k equal from 0 up to n minus 1. Here we had fk times omega to the power minus kj. Okay, but we can write it explicitly this way. So first it's f0 times omega to the power 0 plus f1 times omega to the power minus j plus f2 times omega to the power minus 2j, and so on and so on. The last one is fn minus 1 times omega to the power minus n minus 1 j. But we can write it also this way. This is f0 plus f1 times 1 over omega to the jth power plus f2 times 1 over omega to the jth power and the square of it plus and so on plus f n minus 1 times 1 over the jth power of omega to the n minus 1. And now if we look here and here, we immediately see that this thing is nothing else but f over 1, f on the 1 over jth power of omega, which is exactly what the thesis, what the assertion says. Now for a few minutes let us leave the notion of the Fourier transform, and I will introduce the second notion, which is important for our lecture, and then we will combine these two things together to get the result we are after. Let me define the convolution of two functions and two sequences. And again, I will start with the continuous version, with this traditional standard analytic version. Although we'll use the discrete version, discrete convolution, I start with the analytic convolution because it gives you a proper context. As before, it lets you put the notion in a proper perspective. So if we have a functions f and g, then we define its convolution f star g to be again a function which is defined by the formula that it's f of xi times g on xi minus x. Or f of xi, g of x minus xi. Here the local variable is xi, so we have f of xi and g of x minus xi. If we look at the two arguments, xi and x minus xi, the important thing is if we add them together, we have this local argument, this variable of integration vanishes, it cancels each other, and we are arriving at this x, which we define this convolution. This is important. We'll use it in a moment in a discrete setup. So how we can interpret this formula? Okay, this is some analytic formula that involves integration and may look drastic, complicated, and so on, but it has a very easy, very pleasant interpretation. So assume that f is the function that you have, the graph of f is this left graph, so it's some kind of function. And for simplicity, assume that g is a function which is equal 1 on the interval from 0 to 1 and 0 everywhere else. So it's characteristic function of the interval 0, 1. The convolution of f star g at a given argument, at a given parameter x, is just computed by shifting this graph of g, so it sits at x, and then we compute the integral of the product of these two functions. But since g is 0 outside the single interval, so the product is again 0 outside this interval, so the only non-zero interval is the one from x and to x plus 1. So the value of this convolution at x is just the area of this gray area, this measure of this gray area. And now this is just the value at a single argument. And now when we shift these windows, shift this graph of g, so we slide it along the real line, we compute all the values of the convolution. So we can imagine that this thing slides through the real line, and at every point we compute this convolution, we compute this area, and we compute this area, this integral, and this is the value of this convolution. That's the way we can think about the convolution. And again, as before, here on this lecture we are interested not in the analytic convolution but in the discrete convolution. So we do exactly the same thing that we did for a Fourier transform. We discretize the domain and codomain simultaneously. So in place of two functions, we take two sequences. Now the discrete convolution, which here for a moment I just denote with star hat to distinguish it from the analytic convolution. The discrete convolution is okay, just before we had a integral, so now in place of the integral we have a sum. The sequences are finite, so it does not make sense to sum from minus infinity to plus infinity, because the non-zero elements are only those which correspond to the indices where f and g are defined. So the sum is restricted to this short finite set, and in place of f of xi, g of xi, f of x and g of x minus xi, we have, well, instead of functions, we have the elements of the sequence. So we have fj and g of k minus j. And again, exactly as we had for the analytic convolution, if you look at the two indices, so the counterparts of the arguments, if we add them together, the local variable j cancels. That's the same. That's the same. In the previously we have this psi cancelled, here the j cancelled. That's the discrete convolution. And if you look at this formula, if you look at this formula, you see that this is nothing else but the formula we used to define the to compute the product of two polynomials. So the formula here is just the formula of a product of two polynomials. So what we have is that if we take two polynomials and we treat them as the sequences of coefficients, then the product, the sequence of coefficients of the product, is just the convolution of the two sequences. So the convolution, the discrete convolution, is just a different way of saying a product of polynomials. It's just the same thing but approached from a different direction. Now we have a fundamental identity which is true both in the analytic and discrete cases. So this is true both in the continuous world and in the discrete world. The four fundamental identities says that the Fourier transform and inverse Fourier transform convert convolution to a pointwise multiplication and pointwise multiplication to a convolution. So in whichever direction we take it, we always convert one to each other. So if we start with a convolution and we compute the Fourier transform, we arrive at the pointwise multiplication. If we start with a pointwise multiplication and we compute the Fourier transform, we arrive at the convolution. And it is true whichever we take the analytic Fourier transform and analytic convolution, or a discrete Fourier transform on discrete convolution. Of course, on this lecture here in the computational mathematics, especially in the or generally in the computational mathematics, but in symbolic computation in particular, we are of course interested in the discrete case because the computer memory is finite. In the memory of a computer we can store only finitely many values. So we are actually working in a discrete world because that's the nature of a computer. It's the nature of computations. On computation on a digital computer. And an immediate consequence of these fundamental identities is the following corollary. If we want to compute a product of two polynomials, here the asterisk, the star, denotes the polynomial multiplication and the dot denotes the pointwise multiplication, so multiplication of the corresponding coefficients. What we can do, in place of computing the polynomial multiplication in the standard way, we can use the two identities of these four that we just saw, and we can compute first the Fourier transforms of both polynomials, then multiply them element by element, coefficient by coefficient, just single coefficients, not without doing the whole complicated convolution, just first coefficient by first coefficient, second by second, third by third, just pointwise multiplication of the sequences. Once we do it, we compute the inverse Fourier transform, and the fundamental identity says that this is the same as just multiplying the polynomials. Of course, the complexity of such a multiplication is linear plus the complexity of the discrete Fourier transform, because this pointwise multiplication is just the n multiplication of the coefficients. We just multiply single coefficient, the corresponding coefficients of the two polynomials. So everything which is important is the complexity of the discrete Fourier transform. And now comes the big question, the main question of today's lecture. Can we compute the discrete Fourier transform and the inverse discrete Fourier transform so quickly that the resulting polynomial multiplication will be faster than the Karatsuba multiplication? Recall that the Karatsuba multiplication had complexity n to the power 1.6. It was faster than the long multiplication n square. So the question is, can we beat n to the power 1.6? Can we compute the Fourier transform in such a rapid manner that the resulting algorithm will be faster than Karatsuba? And the answer is yes. Yes, there is such an algorithm. Such an algorithm is called the fast Fourier transform. The fast Fourier transform algorithm was invented or formulated for the first time by Cooley and Takei. However, the origins of this algorithm can be traced back to Gauss papers. So of course in the Gauss didn't use that notion of the algorithm. He didn't use the pseudocode and things like that. He didn't formulate in the form suitable for implementing. However, the main idea was already in the works of Gauss. How this algorithm works? Here, for the didactic reasons, just to simplify the explanation, I will assume that this length n that we deal with is a power of 2. This of course is a simplified version of the algorithm, but it's didactically better. It's easier to explain this algorithm this way. So we'll assume that we have a ring R. We have a power of 2, which we denote capital N, and there exists a primitive root of unity of this degree. Then this algorithm takes a finite sequence of length n and computes its discrete Fourier transform. This algorithm is recursive, and the stopping condition is when the length of f is 1, just a single element, f is just a singleton. If it is a singleton, then the algorithm just does nothing. It returns f. The Fourier transform of a singleton is this singleton, nothing else. We just stop there. In any other case, we split this input sequence into two sequences of half of the length. Here the assumption that n is a power of 2 pays off, because this way we can really split it always in half. If it's f in its power of 2, we are sure that we will be able to split it in half. But how we do the splitting? We just separately take the elements with even indices and elements with odd indices. Here what we are looking for are indices, not the elements itself. The elements may come maybe real numbers or complex numbers or whatever, for which the notion of even odd, of parity, has no meaning, but the indices are just natural numbers, are just positive, non-negative integers, so we can talk about positive, even and odd indices, and that's what we do. We just take even indices, elements with even indices separately, elements with odd indices separately. Now we recursively call this algorithm again for each of these shorter sequences to compute their Fourier transform. When we have this Fourier transform, we recombine them using the formula that the resulting coefficient fj hat is ej plus or minus omega to the power minus j times oj. That's all, and this is the result. So you see that we have two formulas, but very similar to each other. One works for the first half of the sequence, the other works for the second half of the sequence. Before I prove the correctness of this algorithm, let me first show you an example. I will compute exactly the same example as before, so I will take again the sequence 1, 2, 3, 4. So as I said, we start with the sequence 1, 2, 3, 4, the same sequence for which I computed the Fourier transform just by definition, and here we use the Cooley-Takei algorithm. So first we split this sequence into the elements with even and odd indices. The indexing starts from 0, so 1 have index 0, so it's even, and 3 has index 2, so it's even 2, and the elements with odd indices are 2 with index 1 and 4 with index 3. Now these are not singletons, so we split it again. So we have 1, 3, 2, 4, and now we compute the Fourier transforms of these singletons, and here according to the formula the Fourier transform are just identity, nothing changes. So we have 1, 3, 2 and 4, and what we do next, we recombine the elements together. Let me mention what are the, let me show you what are the omegas here. So here the length of the sequence is 1, so omega is the primitive root of unity of degree 1, but the primitive root of unity of degree 1 is 1 again, so this is nothing new. Here we have a sequence of length 2, so the primitive root of unity of degree 2 is -1, and on the whole stuff the primitive root of unity will be I. So how we compute it? Using the formula that you see you saw on in the Cooley-Tucker algorithm, this is 1 plus 3 times omega to the power 0, so 3 times -1 to the power 0, that's first half, and 1 minus 3 times -1 to power 0, this is the second half, and this is here the same, so it's 2 plus 4 times omega, so -1 to the power 0, and 2 minus 4 times omega -1 to the power 0. Of course this is easy to compute, it's 1 plus 3 it's 4, and 1 minus 3 is -2. And here we have 2 plus 4 is 6, and 2 minus 4 is -2. So this is the sequence. And now we need to recombine these two things together. So again using the same formula, however here the omega is equal I, because now we have a sequence of length 4, so the primitive root of unity is I, the fourth primitive root of unity. So what we have 4 plus 6 times omega, so I to the power 0, now -2 plus -2 times omega, so I to the power -1, and now the same but with minuses, so 4 minus 6 times I to the power 0, and -2 minus -2 times I to the power -1, inverse of I. So we can compute this all together, so it's 4 plus 6, it's 10, it's -2 plus, and 1 over I is minus I, so it's minus and minus is plus, so it's -2 plus 2I. Now it's 4 minus 6, so -2, and -2 and minus I, so all together is minus, so -2 minus 2I. So of course the result is exactly the same. That's obvious because we are computing the Fourier transform of exactly the same thing, so it's not surprising that the result is the same. Nevertheless, it's a new way of computing. It's the computing of the Fourier transform using the Cooley-Tucker algorithm. So now when we saw how this algorithm works on an explicit example, it's time to prove the correctness of this algorithm. It's time to prove that this algorithm is really correct. So let me compute the formula for the jth element of the Fourier transform. By the very definition of discrete Fourier transform, this is a sum for k running from 0 to n minus 1 fk times omega to minus kj. And now we'll split this sum into the even and odd parts. We will separately sum over even indices and separately over odd indices. So as in we do exactly what does the algorithm. So now we introduce a new k, so this k runs from 0 to n over 2 minus 1 f 2k. We change the indexation, so we need to adjust it here. Omega to minus 2kj plus sum, and again k is from 0 to n half minus 1 f 2k plus 1 omega to minus 2k plus 1 times j. And what we do next, we just take 1 omega and move it outside the sum. So this can be written in the following way. This is k0 to the power n half minus 1 f 2k omega square to minus kj plus omega to the power minus j, just 1 omega we took out, sum for k equal of 0 to n half minus 1 f 2k plus 1 omega square to power minus kj. But look what we have here. Look what we have here. This part and this part. These are nothing else but the coefficients, the entries, elements of the sequence. This is a kth element of the f even, and this is the kth element of f odd. The length of k even and k odd is half of the length of f, so the corresponding omega is the primitive root of unity of degree half of n, so this is omega square. So this omega square which appear here are the omegas, the primitive root of unity corresponding to the sequences half shorter. So this is exactly what we have in our case. So these are just these two sums are just the coefficients of the Fourier transform of the f even and f odd. So this is nothing else but ej hat and oj hat, and of course here we have omega to the power minus j, oj hat. So this is a proof for the first formula, for the first half. Of course, when this works, as long as j is strictly less than n half, because otherwise we would not be able to index the even and odd parts, because they have half of the length. So this works for j smaller, strictly smaller than n square. So if we have j greater or equal, if j is greater or equal n half, then just change the indexation. Change indexation. We replace j by j minus n half. But look, so the corresponding formula would be f j plus n half equals aj square plus omega to minus j plus n half oj. But let's look here. We have that nth power of omega is 1. So it follows that n half power of omega must be minus 1. So it follows that this thing is aj square plus omega to minus j times minus 1 times oj hat, and this is aj hat minus omega to the minus j oj hat. So this is the formula for the second half of a sequence. So this way we have proved that really the Cooley-Tucker algorithm works. Now the complexity of a Cooley-Tucker algorithm is quite easy to compute. As in the Karatsuba algorithm, we have log 2 of n steps of recursion. The depth of the recursion is log 2 of n, and each time we split the algorithm branches into 2 sub-branches. So we have 2 to this log 2 of n, and so this 2 and this log cancels, and in addition we have this step of recombination when we need to multiply each element of the sequence by the appropriate omega. So this amounts to n such multiplication. So if we took all together, we have n times 2 to the power log 2 of n. 2 and log 2 cancels, and we have log n times log n. So the whole complexity of the Cooley-Tucker algorithm is capital O of n to log n. So as you can see, as I promised, it is faster than the Karatsuba algorithm. Asymptotically, it's much faster. Of course, for small polynomials, for low degree polynomials, the Karatsuba algorithm will be faster. For very small polynomial, the long multiplication will be faster. All these three algorithms has different constant factors, except this asymptotic complexity. There are also these constant factors. So in reality, in the working computer algebra systems, usually all three algorithms are implemented. When we have a small polynomials, then we multiply them using the standard long multiplication. Then when the degree arises, we have certain threshold which need to be defined empirically. When we exceed this threshold, then the Karatsuba multiplication beats the long multiplication. So then the software uses the Karatsuba multiplication. And now when the degree rises even more, then there is another threshold when the Cooley-Tucker algorithm, the Fourier transform based multiplication is even faster, and it beats Karatsuba. So all in all, the fast multiplication algorithm works like this. We have a ring, we have two polynomials over this ring. We select a power of 2 strictly greater than the sum of the two exponents. So we select it in such a way that the result will be possible to be fit into the sequence of length n. And we select a power of 2 because the version of a Cooley-Tucker algorithm we discussed assumed the power of 2. And we select in such a way that we know the primitive root of this degree, or we can compute this. This algorithm takes these two polynomials and returns its product. First, we append to the sequences of coefficients, we append enough zeros so the sequences have length n. So we extend these sequences of coefficients, we extend them by zeros so that we have length n on both of them. Now when we have length n, we can compute the discrete Fourier transforms of both sequences, and we have f hat and g hat, there are Fourier transform of these sequences. Next, the corollary which we saw before says that, okay, we have the Fourier transform, so it's all that we need to do is to multiply this Fourier transform pointwise. So we multiply f0 hat by g0 hat, f1 hat by g1 hat, and so on and so on, f2 hat by g2 hat. So we multiply the corresponding coefficients, corresponding elements of these two sequences, and we arrive at the resulting sequence H, which is the Fourier transform of the product of f and g. So all in all, to recover the product, we just compute the inverse Fourier transform, discrete inverse Fourier transform of f of h, and we denote it lowercase h, and this is the result of a polynomial multiplication. So let me show you this, how it was on an explicit example. Take the following two polynomials: 1 plus 2x plus 3x squared plus 4x cubed, and 2 plus x plus 4x squared plus 3x cubed. Both polynomials are cubic, so the sum of the two degrees is 6. So the next power of 2 is 8. So we append zeros to both sequences of coefficients in such a way that we have sequences, or both these sequences have now length 8. The primitive root of degree of primitive root of unity of degree 8 is square root of 2 over 2 plus I square root of 2 over 2. So we can compute the discrete Fourier transform of both polynomials. Here you see the results rounded to just two digits. And what we do next, we multiply them coefficient wisely. We multiply them one by one. So we multiply 10 by 10, we have 100. We multiply minus 0.41 minus 7.2i times 0.59 minus 6.8i, and so on and so on. We just multiply the corresponding coefficient of f times the corresponding coefficient of g, just pointwise multiplication. And this is the Fourier transform of what we are looking for. All we need to do is compute the inverse Fourier transform, and we compute the inverse Fourier transform. We get the sequence of length 8, so of the form 2, 5, 12, 22, 22, 25, 12, 0, 0. We have two leading zeros, but when we convert this into polynomial, then the leading zeros of the 0 corresponding to x to the power 7 and 0 corresponding to x8, we just drop them, and we have the resulting polynomial of degree 6, which is the product of f and g. So this is the way of this is the fast way of multiplying polynomials. This is the fastest way of multiplying polynomial. So all in all, in these two lectures, you learned the long multiplication, which you know from school, and which is the slowest one. It has asymptotic complexity is quadratic. Then you learn the Karatsuba multiplication, which is asymptotically faster. Its asymptotic complexity is n to the power 1.6, and roughly 1.6. And now we have the fastest one, most complicated, but the asymptotically fastest is Fourier transform based multiplication, which has complexity n log n. To conclude this lecture, let me mention that the Fourier transform and convolution have lots of other applications. On this lecture, I concentrated, we just talked about one particular application, which is fast multiplication of polynomial. but there are hundreds of other applications of convolution and fast Fourier transform. In fact, you have been using this convolution and fast Fourier transform without knowing it for years. Just two other example applications of convolution are the image processing. If you take an image, just digital image by a digital camera, by your cell phone, whatever, and you process it, you sharpen it, you blur it, whatever, many of the filters that are used for processing images, like blurring, sharpening, they are convolution filters. So they compute the convolution of the image. It treats the image as a matrix of pixels, and each pixel is treated as just a value, as a number, or three numbers if it's color picture, and this filter convolves this matrix with a certain kernel. So, for example, one of the basic filters in any image processing program is Gaussian blur. Gaussian blur, which you see here on this screen, just convolve an image with a Gaussian kernel with just standard normal distribution. So this is just a Gaussian blur. Another application of this thing is image scaling. If you resized an image, you take the image and you want to put it online, for example, and you need to reduce its size, then what the internal computer does is it convolves it. It computes a filter that reconstructs the image, resamples the image, and reconstructs and resamples the image. Of course, these two filters are joined together into a single procedure, but the mathematics behind it is just another application of convolution. So this is really thing that is used in many aspects. Just the fast multiplication of polynomials that we mentioned here is one of dozens, hundreds of different applications.
That's all for today. Thank you for your attention and see you again in 2 weeks on the next lecture in this series.